Nuclear fusion is a process in which two atomic nuclei come together to form a heavier nucleus, releasing a significant amount of energy. This process is the opposite of nuclear fission, where a heavy nucleus splits into smaller nuclei. Nuclear fusion is the energy source that powers the Sun and other stars. Key features of nuclear fusion. Fuel. The primary fuel for nuclear fusion is isotopes of hydrogen. In the Sun, the most prevalent fusion reaction involves isotopes of hydrogen, specifically, the fusion of protons, hydrogen nuclei, to form helium nuclei. Energy release. Nuclear fusion releases energy according to Einstein's mass-energy equivalence principle, E equals mc squared, where a small amount of mass is converted into a large amount of energy. The energy release in fusion reactions is due to the difference in mass between the initial particles and the resulting nucleus. High temperature and pressure. Achieving nuclear fusion on Earth requires extremely high temperatures and pressures. In the Sun, these conditions are naturally created by the immense gravitational forces. Fusion reactions in the Sun. The primary fusion reaction in the Sun involves the combination of protons, hydrogen nuclei, to form helium nuclei. This process occurs in the Sun's core, where temperatures reach millions of degrees Celsius. The most common fusion sequence in the Sun involves the proton-proton chain reaction. Nuclear fusion in stars. Gravitational confinement. In stars like the Sun, gravitational forces provide the necessary conditions for nuclear fusion. The immense gravitational pressure at the core creates temperatures and pressures sufficient to initiate fusion reactions. Balance of forces. In stars, the force of gravity pulling matter inward is balanced by the outward pressure generated by nuclear fusion reactions in the core. This equilibrium allows the star to maintain its structure and energy output over long periods. Energy transport. Energy generated in the core through nuclear fusion is transported outward through radiation and convection processes, eventually reaching the star's surface and radiating into space as light and other forms of electromagnetic radiation. Lifetime of stars. The lifetime of a star depends on its mass and the rate of nuclear fusion in its core. Massive stars have higher core temperatures and burn through their nuclear fuel more quickly, leading to shorter lifetimes. Smaller stars, like our Sun, have longer lifetimes. Challenges of achieving nuclear fusion on Earth. High temperature and pressure. Recreating the extreme conditions required for nuclear fusion on Earth is a significant challenge. Temperatures of millions of degrees Celsius are needed to overcome the electrostatic repulsion between positively charged atomic nuclei. Confinement methods. Various confinement methods, such as magnetic confinement, as in tokamaks, and inertial confinement, using lasers, are being explored to achieve the necessary conditions for sustained nuclear fusion reactions on Earth. Energy input versus output. Achieving a net positive energy output, more energy released than input, in controlled fusion reactions on Earth has proven to be difficult. Current experimental fusion devices are still in the research and development phase. Material challenges. The extreme conditions of nuclear fusion, including high temperatures and neutron radiation, pose challenges for materials that can withstand such harsh environments over extended periods. Researchers and scientists are actively working on experimental fusion devices, such as the ITER, International Thermonuclear Experimental Reactor, project, to explore the feasibility of controlled nuclear fusion for practical energy generation on Earth. If successful, nuclear fusion has the potential to provide a virtually limitless, clean, and sustainable source of energy.